Sir, you are muted. Hello, sir.
Yeah, it's okay now, right?
Yes, sir.
Okay, and slide visible, right?
Yes, sir.
Okay, fine. So we continue today this. Yeah. So uh, starting from yesterday's class, so quantum mechanically uh, one can detect sub-Poissonian sources, and photon count you can do. And we have shown this experimental setup which actually helps to what do you call that, to find out the efficiency, quantum efficiency, and quantum efficiency of the detector. So for that we this experimental setup is laser source, and then slight one beam splitter you will be using, and from that some light you will be tapping, maybe some 1% to 2%, and you can actually measure the intensity or power directly in a conventional power meter. And major portion you pass through your attenuators. It should be variable optical attenuator, and then this variable optical attenuator will attenuate at a different level, and then finally the output from the attenuator, if the power coming out of the attenuator is P, and mind that this is a continuous wave laser, no pulse, nothing. So in that case you can calculate the incident rate of the photon will be calculated according to this one, P lambda by AC or P by H nu. And then for a given time instant, some tau, time sampling time, say it can be your dead time also of the photo detector. The number of photons in this experimental setup, it is considered as a mu, as a n bar. That should be whatever our incident is there, and you have to multiply by time, how much time it is coming. So that can be considered as a average number. So this P you can directly calculate from here. Suppose if it is 10% coming here, that means you can, whatever power you are getting, then 100% how much that P will come here. So accordingly you get your calculated average photon numbers coming to your photo detector, or 90% or whatever attenuation is there, that attenuation value you can consider. By attenuating this controlling this variable optical attenuator, you can control mu or n bar. So different level of things are there. Now if you see the experimental results, this detected detection rate as a function of the average number, this you are varying here, and accordingly you are putting in x-axis, and detection rate in the photo detector, whatever you get, if you see the experimental results, it will be looking like this. So now from here, whatever the value, you are getting this curve, and we have shown that that is a d here, and this is a 1 by tau. That means the detection rate is just inverse of the dead time, because beyond that it will not be able to count. Even though your photon number is increasing, and the things will not be counted, and this will be your initial values. Even your zero average number, you see something that is actually dark current, dark counts, and dark counts will be very slightly, it will be again following here. That's I mean to say, if you are increasing the mu value, initially it will not increase, and then it will be increasing like this, and then saturate. So it is not like that. what our theory says about this detection. Okay, so about this detection, if you try to see, you have we have just discussed this one, right? That is actually the n bar in the detector. Detector means average detection. Mu is the average incident photon, right? Mu is the average incident photon, and your eta is the efficiency. Then eta times mu will be the average number of photon number detected. Okay, that n bar actually we have discussed earlier, right? This meaning this n bar, whatever we are talking about, n bar means eta times n bar. That's how we are getting this quantum efficiency. It is called intrinsic quantum efficiency, of course. Okay, this eta mu, that means you are considering a time sample or getting window is very small, so mu will be small and multiplied by eta will be so small that it can be less than 1. That means less than much less than 1 photon. That means sometimes it may come much less than 1 photons, means it's not a fraction. It overall it says that photon will be there and many times it will not be there. That is how we get in terms of eta times mu is less than 1, because we'll be normally we'll be discussing the photon statistics from just classical semi-classical point of view, right? So in this type of situation, the count rate of an ideal detector means it will have some eta value, but no other, like you don't have anything delay, dead time, instantaneous things happens, and also no dark currents, no noise, everything. That is what is called ideal. Ideal does not mean here eta equal to 1. Okay, eta can be some value, it can have some value, but other thing, electronics related noise, everything is not there, absent. So that ideal detector, and for a Poissonian distribution, so detection rate can be expressed like this. So can you explain this one? I have just written 1 minus this one. What does it mean? The second term, anyone can explain? What is this? May I ask someone? What about Murali Krishnan?
So it's 1 minus 0 photon getting detected.
Yeah, so it is actually Poissonian distribution, right? To obtain eta mu is the average number n. Whatever this n bar, it comes in the we have already discussed earlier, no? That's this thing. This is the detection of a photodetector. It is anyway Poissonian, right? So to find a zero photon, to detect a zero count. So because your n bar, instead of n bar, we are writing here capital N bar. So capital N bar is eta times mu to the power 0, 0 factorial, and e to the power n bar, capital N bar means eta mu. So this is the probability of getting 0. And you know that for any window of time tau, it is so small that either it will be 0 or maximum at max it can have one photon. So you can say that if this is the probability of finding a photon, a 0 photon, then what is the probability of finding 1 photon? Then you can just say that 1 minus this one. That is the simply we are writing like this. And then if this is the probability, and that probability for a time window tau, then rate will be divided by tau. Okay, so this is how we say that the detection rate at your photo detector, that actually following the Gaussian rule that we have explained earlier. Now since we have assumed that this eta mu equal to much less than 1, hardly you will find a photon in that window. So this this is obviously, this thing is coming as 1, right? And then this e to the power eta mu, you can expand, since it is less than 1, just you take first two terms of the exponential. So 1 minus eta mu. Okay, so in that case you get detection rate approximately 1 cancel, and then it is just eta mu by tau. So if you're sampling this tau, it's just any time window you are measuring. We are considering that no dark, no dead time, nothing is there. Okay, and this is even though we are considering same symbol, it is just you consider as a time window you are measuring. So in that case, what is the detection rate? Now we see, if your detection rate will be proportional to average number of photons, because eta is constant and time sample you are considering as a constant. So your count rate at the photo detector, that will be eta times mu. So this count rate means you should always keep in mind, this count rate means it is not like one photon comes and one electron hole pair generates and you are detecting only one electron. Instead of that, what you have, a pulse of electrons will be, avalanche process will happen, and that pulse you are measuring, current pulse you are measuring. One photon means it will as a output giving one pulse, and one pulse means one count. One pulse of current is one count. So that one count, that count is this one, and that count will be, it's obviously it is proportional to your mu. That means what is the average photons coming within that time slot, right? So ideally it is say approximately it is shown as a, when this is brought down to a single photon level and that eta mu is less. So all these conditions will be there. So our ultimate goal is that if we can separate one particular photon and detect what is the efficiency of detecting a single photon, even though you can have a very ideal source, then whether you can detect perfectly and how much accuracy will be there, that is our goal to understand now. Okay, so we know that that is a proportional to mu. So in that case, so this thing, ideally what you should get, if you are taking log mu time log r detected, what would be the curve look like? Anyone can tell? This is your experimental, but for ideal case you supposed to get this one. So ideally, what would be the nature of your curve? Sharad? Sharad, can you tell? Yeah, I'm asking you a question. Can you tell me? I think you. No? So I think you are noisy. Somehow I don't know. Where are you? You are from mobile or where? I don't know. Anyway. Huh?
Laptop only, sir.
Rectangular?
No, sir. No, sir. I'm from.
No. What is the curve nature it will be for ideal case? As a function of, if you are plotting log of R detection as a function of log of mu. Are you following my class?
Yes, sir.
Then you should be able to answer. Anyone can help? Gantashala, can you tell me?
Hello, sir.
What would be the nature?
A straight line, sir. Log R is equals
Yeah,
to
it should be just
log eta plus log mu.
So it should be a straight line. That's a, even if you just plot R detected as a function of mu, it will be straight line. So it log scale, it will be both side log, it will be also straight line. But instead of that, you are getting like this, and that is because of the all things happens. In this case, you are considering that whatever coming and instantaneously you are measuring. But if you have a date time tau and dark count is there, for example, where from this dark count comes, that's a thing is that again, whenever one count will be registered only if you have a pulse of electron current pulse is generated. That means that current pulse will generate, avalanche process will take place if somehow some electrons are there. For example, you have a photodetector and you have one electron coming, one photon coming, and then you have electron hole pair generators, and that because of the avalanche process a large number of electrons will be generated, and that is your current. But somehow out of that large electron what is generated from the previous pulse, previous photon, somehow one electron may be trapped somewhere in your device, semiconductor, it's a photodiode or anything, it is somewhere, it is trapped, and when it is trapped it may be able to release after some time when that pulse already gone. So when that electron comes out, that can again generate another pulse. So that is one way of, because of this this is sometimes called after pulsing. After pulsing another count can come. That is also can be counted as a dark current and dark count. And another thing is that any stray photon can come, also can generate randomly. Okay, so for that purpose you are getting this type of experimental results. Okay, so when you are getting experimental results, then we need to know then that this is deviating from this expression. We need to know what is the real count, subtracting dark count and considering the date time. So that true detection, actually you can calculate whatever value you are getting in your measurement. This art detection is now not this art detection. This is art detection means detected count, your experimental results. Okay, experimental results, because in the experimental result you have included dark count and also the tau limitations are there. That one divided by whatever the, for that date time, whatever the total count that you subtract -1, and that is actually gives you the date time related count, and the dark count you have to subtract in a same fashion. So this is the expression. I have not put much thought how it comes exactly, derivations, because I have copied from some paper published in Nature. I think probably if we give a little thought, we will be able to explain where from this coming. This is obviously coming from this delayed time, whatever detection possibilities there, some kind of probabilistic things are there. But I suggest that you guys also take as a assignment to derive this. What would be the true? What I mean to say that you try to prove this, that true detection rate will be expressed by this formula when D is the dark count rate and tau is the date time of the photodetector. Date time of the photodetector means within that time any other photon comes, that will not be considered. So within that tau, any two successive photon comes, then it will not be able to resolve. So in that sense, the true detection time will be there. I've just copied from that paper. Probably I will give that paper to you all as a reading assignment. You try to solve. I also suggest Ramon and Arnab also look into it, because I little bit I thought it, but I could not find out what is the things. But this is an important parameter. Most of the people they are using to find out actual detection rate. Okay, so now if this is the detection rate, now what is the efficiency then? So efficiency you can calculate. What is incident? You have to normalize this true detection rate with incident photon. Incident photon, what is the expression we have derived? We have this incident photon is this one. This is the incident photon number. Sorry. Yes. So incident, this one actually, I think mu by tau. Tau by mu will be there. And tau by mu, yeah. So eta times mu. So if you just take a ratio of this one, then you get this R true detection by R incidence. R incidence means whatever things you are coming here in n things coming here, n bar. So yes, eta times mu. So this is your detection that is there, and tau by mu. So this is the actual things coming. So eta will be tau by mu times r detection. So that is actually incident. So this expression comes. Actually from this you just find this efficiency, right? I think this is correct, I think, right? So this will be tau by mu times this one, that is the eta, right? I have a little bit confusion here. This one here, r incidence equal to mu by tau, right? R incidence multiplied by tau equal to mu. So R incidence equal to mu by tau. Okay. So R incidence equal to mu by tau it comes, and true is this one. So tau by mu. That's correct then. Yeah. So this is the efficiency. Then these parameters from this, once we know the R detected value and you know the dark count, that parameter you need to know. And also you can find out that one, this eta mu tau from the experimentals can be determined by analyzing the experimental results. So once the experimental results there, you know what is the dark count and when it is saturation, that means it is one. Excuse me, this is 1 by tau. So tau is known from the saturation value here, this one, and dark count found here. Then once we know dark count and tau, then whatever the exact measurement value is there, with that you can calculate actually the efficiency. So that was the ultimate goal, that to know the efficiency of the single photon detector, photon counter. That is actually this expression. Okay. Now,
Sir,
yes.
in the previous slide, if we bring eta to the denominator,
Right.
then we'll get our like both the count rates in this slide. Like we'll get 319 is equal to 320 in that case equations.
No, this is here we have not used a dark count.
Yeah. Like we got the second one considering dark count rate.
Right.
But in 321, if we divide by eta.
No, we are finding the eta. Eta is defined by this.
Yeah. So suppose suppose we divide the whole equation by eta. Whole 321 by eta.
Right.
Then we'll get equation 320.
This is the expression of eta. No, you just this is the eta value, right?
Yeah.
Eta we define this one. So I put this expression first.
Yeah.
Now I need to know what is the value of R incident.
Yeah. That
So
is mu by tau.
Mu by tau.
Yeah.
R incidence mu by. That is how tau by mu comes.
Yeah. But according to equation 321, if we see actually.
Suppose you consider that okay. Okay. I understand what you mean by say that whether 321 and 319 is actually following. Suppose your tau equal to 0 and d equal to 0.
Okay.
That means your dead time is 0. That means instantaneously it can count. That means this term goes and this term also goes. Right? Dark count is 0.
Yeah.
Then it is following this equation 319.
Yeah.
That is what you wanted to know, right?
Actually, I observed that according to equation 321, 319 and 320 are coming as equivalent.
320 and 321 is coming like equivalent.
319 and 320.
Yeah. I think because 319, whenever
it's
I'm
an
saying,
approximate one.
No, that is not approximate. 319 is the ideal case. Approximation consider when eta mu less than 1. So
Yeah.
So if it is this tau is I think you don't confuse with this tau with a date time.
Okay, both the taus are different.
This is just arbitrary time, sampling
yeah.
time. I
Sampling
mentioned
time.
that, sampling time.
Yeah.
So
Okay.
if you just consider that arbitrary sampling time, then it is fine actually. But in this
Yeah.
expression, this tau is actual date time.
Okay.
Actual date time. And then you are calculating here also, whatever you are putting, they are actually this tau you are considering, the sampling time you are using here. Okay.
Yeah.
Okay.
So only if sampling time and dead time are same,
That
we equal.
then right exactly.
Okay.
So basically, if your every pulse, if you have a single photon, normally it would be better your sampling time should be like a dead time at least. Our frequency should be such that it should cover up that thing. So that thing you have to mention, as I mentioned earlier also, because within that another pulse comes within dead time and photon is there, for example, you will not be able to see. Okay.
Yeah.
Right. So next thing is that if this is whatever we have discussed here, you are considering a continuous wave laser, right? Sometimes for example, single photon generation on demand, etc., you can actually, you have to use a pulsed laser. So normally you are just sending a pulse, and that pulse laser, if you use to find out your efficiency, it's a straightforward case. That frequency should be again much less than your 1 by tau. 1 by tau is the dead time. Whenever you are using pulsed laser, that pulsed laser frequency, that pulse frequency repetition rate frequency should be sufficiently low so that every pulse comes after the dead time of the photodetector. Okay. Then in that case, a mean photon number per pulse, mu, it is known. For example, you can find what is the mean mean photon number within that pulse, right? The rate of incident photon number and the detection rate of the ideal case can be written as, you see, the incident photon number will be mu times frequency, repetition rate. So every pulse you have a mu number, and if you multiply the frequency, then incident rate, overall incident rate, you can calculate onto the photodetector. You know, this is a per second, and this is average number. So per second one pulse comes, for whatever the second, that many number of pulse comes. So if you just multiply that, then you can get the rate of incident, as if it is like a, this incident is similar to that of CW. If you are just having mu multiplied by repetition rate, then this incident rate is same as this expression. Okay. If you know the mu value and then frequency rate, that will be actually same values. So it is just made equivalent to CW, continuous wave, instead of pulse. And then our detection, again, same fashion you write, right? 1 minus whatever the thing here you have calculated, right? That detection, ideal case detection, 1 over tau, all these type of things you are getting. So here also 1 minus mu, and instead of 1 over tau, you are writing a frequency. That means repetition rate. That is actually detection rate. Detection rate will be coming. So repetition rate, if you just multiply, instead of time sample, you are calculating, you are dividing, you will just have a repetition rate. If you multiply, then you get the detection rate. Ideal case, f eta mu. So this will be 1 minus again eta mu, like same way here, whatever we have written like this fashion. So we get f times f. So there you get eta mu by tau, because tau is the sampling time. Instead of that, this your sampling time like coming as a pulse frequency you are getting. So f eta mu. Okay. So in that way, if we just try to find out again the considering the dark current, date time, all those, if you just consider, then your efficiency will be detection efficiency will be like this. Okay, just same thing like R2, whatever the true detection you are getting, this one, this will be true detection, and then divided by R incidence. Just R incidence again, you just put down here mu times F, R incidence coming, that one is this one. So here few notes you should consider, because whenever you are doing some experiment with a single photon detector, so whatever eta we are calculating, we are just showing here, it is actually looks like that the experiment to derivation, it is like that intrinsic quantum efficiency. That means how many photons are coming, and out of that many photons, how many photons are affecting the photodetector. Okay, that is how eta is there. That is called intrinsic quantum efficiency. Whenever we just write down this expression, n bar equal to eta times mu, that means it is called intrinsic quantum efficiency. So that many photon number, this fraction number will be contributing to your count. Okay, but you have always some practical limit. Practical detection efficiency eta must include the optical coupling efficiency. So you know your photon streams are coming, but you have earlier also I discussed that your area, how much area is there, whether entire all the beam is falling onto the surface of the detector, or if you are using a optical fiber. Okay, optical fiber, say you know that is a core size is about 10 micron. That 10 micron core size should actually completely hit coupled to the photodetector surface. Otherwise there will be some kind of coupling loss. Or if it is a waveguide, if you have a single photon detector, you are just integrating on chip, all the integrated circuit is there, and then single photon detector is there, and single photon detector geometry will be different. So your waveguide geometry cross section and single photon detector cross section and overlap will be maybe different. So in that case, some additional loss will be there. Obviously there will be some mismatch will be there. So that loss, if you convert into, suppose if it is 90% is overlapping to the photodetector with the beam, then your eta loss will be 0.9, for example. Okay, if it is 80%, then it will be 0.8. So in that case, overall loss, overall efficiency of the system, including coupling, so you should multiply eta loss time eta detected. Okay, whatever the things are, efficiency or quantum efficiency. Okay, so overall things are, if it is quantum intrinsic quantum efficiency is 80% and loss is say 40% or something like that, then 0.8 times 0.8, that means 0.32 will be your ultimate quantum efficiency, much lower. So that thing you should keep in mind. And then one thing is that when eta is measured accurately, the date time tau of the detector and the counting electronics must be considered. So date time for the detector, the date time not only for your detector always we say that after one things, whenever it is releasing and next photon, it should relax back. The internal dynamics mechanism should be stabilized again, so that it can come to it can set to its initial point. So that is whatever we are talking about detector. But other than that, your electronics is there outside, bias electronics, everything is there. So current should there can be some delay also. That delay also can be counted into your dead time. This intrinsic dead time as well as your outside electronics dead time, that should be also counted. Total things, overall delay has to be considered. And the and final thing is that the major count rate of the detector or detection should be corrected for the finite dark count rate, all this type of things. So dark count rate you have to count, and date time also you have to consider. These three things basically. This coupling loss to be added, and you should consider, that is what in the expression, all the expression, if you see d and tau is also there. So this is just summarized here in 3 points. And then another thing is the timing jitter. Okay, so timing jitter is the another important parameter. That is how we we have to decide that exact timing of your arrival of the photo detector. For example, I want to know the incoming photon statistics, whether they are coming in a regular interval, or if they are not coming in a regular interval, what is their what do you call that? What is their distribution? So if it is Poissonian, sub-Poissonian, super-Poissonian, or it's another type of sub-Poissonian squeezed light, all those type of things are there that we have to measure accurately. But one thing is that, as I mentioned earlier, your detector, a photon comes, energy, what happens actually, inside the photo detector, if you try to understand the physics, what happens, their electron hole pair will be generated. That electron hole pair will not be generated instantaneously. Why is that? Because ultimately this incoming field, electromagnetic field, it actually imparts some force onto a electron which is already in the valence band. And incoming electric field, it has a high frequency. Electric field is oscillating with its optical frequency, right? And then your electron bound to the valence band, that will actually start oscillating with the frequency of electric field associated to a electromagnetic wave. And then once it is start oscillating, if it somehow resonant to the band gap, the entire energy, one quantum of energy, then it can absorb, and then it can go to the conduction band. So this timing, that incoming photon to electron hole pair generating, and then that electron generation of electron, again it will undergo through avalanche process. That pulse will be generated. Once the pulse generated and measured in the output load, then your count is complete. So this entire process, it is not that all the time will take, because it is internal mechanisms is there, internal physics is there, some defects, some where exactly photon is hitting in your, you have a photo detector, that area is suppose in the order of some few micron cross section, but your photon coming, and that you don't know where actually that photon actually hitting on the photo detector. So if it is a different point, if it is hitting, and different type of internal crystallographic structure, defects, and deformations, and internal field, all those type of things are there. Depending on that, your generation of electron pulse may delay photon to photon, right? So that means, and it is not necessarily that it is uniformly delayed for every photon, no. So that actually depends on, again, some kind of noise inside the detector. So that actually, that timing difference is called your jitter, timing jitter. Okay, suppose you know that you want to find out a particular photon, how it is photon to photon, how much it can vary, that variation, that jitter variation, that timing variation. If you want to know, then what you do, you use a very pulsed laser source, maybe femtosecond laser or picosecond laser. That means your pulse duration will be very small, duration pulse will be there, and picosecond normally it is good enough for this type of detector. And then you have one normal classical fast photo detector will be there, one part it will be hitting, and another part will go through normal single detector, and then there will be some kind of delay line will be there. This delay can be controlled here. Okay, delay means some path length difference. You can delay the signal. After detection, you can, let's say, electrical delay lines can be there. And then you can actually just start and stop triggering some certain time window you try to measure. Within that time window, you see that one photon, the signal coming here, whatever the pulse laser signal coming here, because it is a very fast detector, you are measuring here. With that delay you can control, and here through this, any one single photon coming, for example, it is an attenuator, you are bringing down to a single photon level approximately, then you try to relate the timing. Okay, then with that timing and different count, if you just measure a histogram as a histogram, then you find that they are arriving at a different time, although because we are considering one pulse will contain one photon maximum, if at all is there, you are attenuating in that level. Okay, 0 or 1 photon, most of the time can be 0, that is fine also. But whenever one photon is coming and you just correlate with this one, then you try to measure the histogram as a timing, exact timing when it is arrival time, you just note it down. So here actually in this thing, 3 different, this curve, if you see the 3 different photo detector. The first one is the so-called silicon avalanche photo detector, silicon SPAD, silicon single photon avalanche detectors. This is called SPAD, SPAD, single photon avalanche detector, SPAD. So that is commonly used for a conventional way, particularly the visible region silicon photo detectors are good. And this is some additional engineer, this blue curve, engineer this silicon SPAD, but engineer one. So in that case, you see that the jitter timing, that means FWHM, if you see, you expect that it should come exactly at that particular time, deviation 0 we are considering, right? But you see the deviations like this thing. For example, if you see the full width maximum here, this is the count you are getting. Count, if you are just calculating, then this full width maxima, I think this is minus 500, so about more than 500 or around 500 picosecond. But if you just control, you just your shallow, I think this is a special type of photo detector they are measured. So where actually you could actually make a little bit faster, so and jitter can be reduced, then this FWHM can be reduced. And this is what this is the Gaussian type things, whatever you get. This is the red color one. Red color one is the latest development, that is called single photon detector, called SNSPD, single photon superconducting nanowire single photon detector, SNSPD. So superconducting, S stand for superconducting and N stand for nanowire, and SPD single photon detector. Okay, so there actually your jitter is much lower. So exact timing you can say. So once you know the jitter, actually you can actually predict that, okay, my jitter is within this limit, and so what is the expected value could be, you can predict. So all this instrumentation and this device technology limitations you have to consider when you are designing a quantum photonics device. I will just take, I want to take one more class for this photo detector. Final figure of merit I will be discussing, and also probably I will be just explaining how experimentally one can measure this correlated photons. If 2 photons are coming, they are correlated and entangled photon. Entanglement, though I have not discussed in details, that will be followed. But this photo detector part to complete, I will discuss one more. I will take one more class on that, and yeah. So I stop here.